Alright, so we have to perform first of all is the mass balance, okay, using the stoichiometric equation. So here we have ethanol, which is actually dehydrogenated. So you see that this hydrogen is coming out, okay, being removed away from here, and then it produces hydrogen as well as acetaldehyde. So first of all, we need to check whether the stoichiometry is balanced. So you can see here there are 2 carbon atom, and then there are 6 hydrogen atom. So similarly, we have here 2 carbon atom, 3 plus 1 4 plus 2 6, and then 1 atom of oxygen. Alright, so this is balanced. And then we look at the inlet part. The inlet part is actually we have 90 mole percent of ethanol, and because we want to make sure that the product is being driven, okay, the product is being driven to the outlet, to the intended product, okay. So we want the intended product, so we put little bit amount of acetaldehyde here, just to make sure that all the ethanol will be, some of the ethanol will be converted to acetaldehyde here, and it will reduce the amount of ethanol here, okay, so that you will achieve higher conversion. And then the flow rate given is 150 mole per second. There is an additional heat because we want to maintain the temperature at 250 degrees Celsius. We don't want the temperature here drop too much, okay. So that's why we provide some heat here, because this is an endothermic reaction. Coming to the next slide, actually we are looking at how after we do the material balance. So we realize that actually, because this is something that we do not know much about the heat of reaction for this particular reaction, so it will be easier for us to actually come out with what we call as elemental balance. So we're going to use heat of formation method here, okay, heat of formation method here. We need to perform the mass balance again, but bear in mind that it's also 10% of acetaldehyde, CH3, it's supposed to be CH3, CHO as feed to the reactor 2, and there are ethanol which is not completely reacted in the outlet. So here we have this particular equation, stoichiometric balance. So we need to do some kind of elemental balance here. Alright, for example, we start with carbon balance. So carbon balance here we have 0.9, 90% in ethanol, multiply with 150 mole per second, multiply with 2 because we have 2 carbon balance, plus 0.1 times 150 times 2, because also in acetaldehyde we have something inlet, but it is only 10%, and it also have 2 carbon atoms inside acetaldehyde. But then we do not know how much actually ethanol left here, okay, outside here, and we do not know how much is actually the acetaldehyde here. So but then we know that the carbon atom definitely will be 2 in ethanol, and the acetaldehyde definitely will be 2 in acetaldehyde. So it is N1 times 2 and plus N2 plus times 2. If we simplify further, we'll get that N1 plus N2 is equals to 150. Okay, so we have equation 1. And now we do the hydrogen balance. The H balance is, we have in ethanol we have 6 hydrogen atoms. So here 0.9 multiply with 150 multiply with 6, plus 0.1 multiply with 150 multiply with 4, because we have 3 plus 1 4 as the inlet. And then here we have hydrogen in all 3 components. So if you could remember here in the previous slides that we have N1 is ethanol, N2 is acetaldehyde, and N3 is hydrogen. Okay, so we have here N1 is ethanol, which is 6 hydrogen atoms. In acetaldehyde we have 4, and in hydrogen we have 2. So we simplify further, we'll be able to get this equation, 3N1 plus 2N2 plus N3 equals to 435. So this is equation 2. Okay. The next thing that we have to do is we create what we call as input inlet outlet enthalpy table. Okay, so we have here ethanol and acetaldehyde coming in. We know the number of moles here because it was given, and then we need to know the H1. H2 at 300 degrees Celsius, both of it. And we know that the outlet product is 253 degrees Celsius. We didn't know what is single outlet for each of this. For example, how much ethanol here, how much acetaldehyde, and how much hydrogen here. And we also need to calculate the enthalpy H3, H4, and H5 at 253 degrees Celsius. Okay. So the next part is actually how we look at solving it. Alright. So from the enthalpy table, we know that ethanol, okay, if you remember the equation earlier that I shared with you, H input for species is actually the standard heat of formation, okay, plus the integral from 298, which is at 25 degrees Celsius, to the temperature of the input. Here, if you remember, it is at 300 degrees Celsius. So that's why we become 573 Kelvin. So, and for H output is the same, except that now the temperature is actually at 250 degrees Celsius. So now it becomes 526 Kelvin. Okay. So when you find from the table B1, so if you look from table B1, acetaldehyde here, the heat of formation is given as negative 166.2, and ethanol is actually 277.63 and 235.31. So which one that actually we wanted to use? Okay, because now this is the tricky part, because we know that ethanol is actually at 300 degrees Celsius, so definitely it is in gas. Okay, it is no longer in liquid. So we pick this 235.31. So when we go back to this table, then we pick that particular value 235.63, which is I think a little bit different here, but it's the same. And 166.2, so we insert here and we calculate the CPDT, which is from 298 to 573, as well as from 298 to 526. So we can calculate the H input and H output here. I would like you to do on your own, calculating the H input value here. Okay, but H output is being given for ethanol, for acetaldehyde, as well as for the hydrogen. Why hydrogen there is no heat formation? Because it is elemental. Okay, hydrogen is at its own elements, so that's why there is no heat of formation. Similar goes to oxygen, similar goes to nitrogen. Okay, so there is no heat of formation for those things, so the value is equals to 0. Okay, but for others, then you have to calculate. For H input for hydrogen, there is no H input for hydrogen, so this is 0 here. Okay. So